Now, do you all know where to find the videos? They're on modules, Unit 1, Unit 2, etc. Okay. Oh, there's a handout. Sure. Grab 2. Give him one on the way. Handout. Okay. Last time we talked about the periodic table and what those numbers mean on the periodic table. There's always a integer, and 99% of the time there's a decimal number on there. The decimal number refers to the average of all the isotopes that reside in our world. Sometimes there's a name, there's always a symbol. It's either 1 or 2 characters. The first character is always uppercase, no exceptions. The second one is always lowercase, no exceptions. For example, cobalt is CO, so it would be big C, little o. So some of you write with uppercase on everything. I had a Coast Guard guy that was in a class of mine about 10 years ago. And by international law, he had to write in uppercase on everything. And he'd been doing that for like 12 years. So he was in a habit of writing uppercase. I said, sorry. So anyway, and then this is the average. Now, normally, when we write a chemical, an element, we refer to the isotope number and the number of protons in the reverse way that they typically appear on the periodic table. So what goes? So like this boron here, on the periodic table, the 5 is on top, not the bottom, but only on the periodic table. And they've been doing this for 150 years, and they switched to this protocol a long time ago, but they kept it on the periodic table. That was a bone of confusion last time. Okay, so the number on the top is the isotope. So this would be boron 11. Boron has 5 protons, and if this is neutral, it also has 5 electrons. And then today I'm going to talk about what if it's not equal, and we have an ion. Okay, so that's what we did, and this worksheet is available on Canvas files. Okay, so let's do one with a neutral atom here real fast, just for review. Okay, so let's do this one here. Atomic number 11. So what does that correspond to on the periodic table? It corresponds to sodium, Na. And the atomic number is the same as the number of protons. So that number goes on the bottom. And these two are always equal, atomic number of protons. The electrons are the same as protons if it's neutral. And to find the number of neutrons, we need to look at the atomic mass, or the isotope number. That isotope number is the sum of protons plus neutrons. So we have 11 plus what is 24, that's 13. And then this is sodium isotope 24. Now the atomic mass or the isotope is always an integer, no exceptions. Your periodic table has got a decimal number on there That is the average of all the isotope. That's why it's a decimal number. So a lot of people mistakenly put the decimal number of that element over here. And this is a very specific integer and a specific isotope. And the reason why it's always an integer is you can't have a fraction of a proton added to a fraction of a neutron. Those are whole numbers. That's why this is always whole or an integer. Okay. All right. So hopefully all of you practice that. Hand up. All right. So what happens now? Are there any questions about this worksheet? If you download it, it's got the answers for the second page. Okay. So yeah. Okay. It's because it's an ion. Oh. I'm going to hit that in detail in a second. It's okay. Attention to detail is important. All right. So this is the situation frequently. Now, in nature, it's rare that you find an element by itself. The elements you find by themselves are the noble gases over here on the far right of this. Over here, far right. Remember, those are noble gases? Those are the elements you find by themselves. And the reason why you find them by themselves is they're very stable. The rest of the elements from the noble gases to the left are not stable. So they want to become more stable by combining with other things. That's how they reach stability. So, and again, this is a platitude in my class. Everything goes from unstable to stable, not the other way around, unless you supply energy. If you supply energy, you can take something that's stable and make it unstable. For example, these fluorescent lights is a perfect example of doing that. So what we're doing this fluorescent light, we're taking a nice stable electron and jacking it up to a higher orbital that's unstable. And that electron doesn't want to be there. What does it do? It wants to come back down to a more stable orbital. And when it does that, it gives off energy, the same amount of energy it took to get up there. And that energy is in the form of visible light. That's why we see it. LEDs, lasers, fluorescent lights. All those are examples of taking something stable, making it unstable, and let it come back down to a more stable state and give off energy. Capacitors, storage of energy from solar panels. People that don't like solar, they say, well, at night you don't get solar. Well, you store it during the day or you sell it back to the power grid and you get energy at night. And they frequently, if you're remote and you can't sell it back to the power company, you store it overnight with something called a capacitor or a battery. Capacitors are much cheaper than batteries. A capacitor stores energy. If you took a microchip apart at a microscopic level, you would see it contains capacitors. It also contains coils and transistors. And we're talking like at the millionth level scale. Microcircuits are extremely small. When I was in high school, I was an amateur radio operator, and I worked for McClellan when it was still an Air Force base. I used to be part of the military affiliate radio system. And I used to build my own equipment. It was my hobby. I built transmitters, and I didn't build receivers because they're much more expensive, but I built my own transmitters. And everything was big, giant vacuum tubes. That's how old I am. And so a vacuum tube for a transmitter can be this big. Nowadays, take out your phone and it transmits also. And there's nothing that big in that phone. That vacuum tube is bigger than the phone. And another thing, that vacuum tube used a ton of electricity because it got hot. So in the wintertime, it was great. You just turn on your transmitter and you warm up your office. So anyway, these capacitors store energy as part of a circuit, and they're very efficient. Okay. getting back to what I was talking about periodic table. Noble gases are stable. You'll find them by themselves. Everything else has to combine to be more stable. There's some exceptions there. For example, what about gold and silver? You find gold, right? Well, the reason why you don't find very much of it is because it's in a stable format, but it's hard to get there. Same with silver. A lot of the metals, nickel, copper, zinc, you don't find in nature. Iron, the early ancestors got iron from meteorites. It's a museum event. So anyway, so what happens is frequently the elements that are not part of the noble gases are tied up with oxygen. They're called oxides. Like uranium's uranium oxide. Iron, it's called rust. Zinc, zinc oxide. What else? All of them are tied up. Carbon, carbon dioxide, carbon monoxide. Something interesting about carbon, this is an aside. Carbon is just pure, a diamond is pure carbon. So is a charcoal briquette, pure carbon. Do they look the same? Not by a long shot. Guess which one is more stable? I'm setting you up. Which do you think is more stable? The what? I mean, yes, it's the charcoal is more stable, believe it or not. So basically, when you buy a diamond ring, it is not very stable compared to a charcoal briquette. So your diamond ring is eventually going to go away and going to rub off and become carbon. Now, from a thermodynamic standpoint, that's true. From a kinetic standpoint, it's not true. It takes a really long time for that unstable diamond to convert over to charcoal. But believe it or not, the diamond is less stable than a chunk of charcoal. Now, I didn't know that until I had to give a presentation on that. I was surprised. I went, to me, it's not intuitive at all. But anyway, all right. So, so most of these guys over here are tied up with oxygen in general. Sometimes it's with a halogen like table salt, sodium chloride, but they're tied up because they're by themselves, they're basically unstable. And some of you might say, well, what about chlorine gas? That's Cl2. These are two of them, though. You don't find chlorine by itself. It's always as an ion. And that ion wants to pair up with another ion to form a stable compound. Okay, so ions. When the number of protons does not equal the number of electrons, that's considered an ion. When they're equal, it's considered a neutral atom. And there are more ions in the world than neutral atoms. So there are two situations. If the number of protons are greater than electrons, it ends up being a positive charge. And it's called a cation. And it gets its name cation from they're attracted to the cathode of a battery inside the battery. That's where the cat part comes from. And then an ion. If the number of electrons is greater than the number of protons, it has a net negative charge, and that's called an anion. And these are attracted inside the battery to the anode. That's where this comes from. Now, a good way to remember this is think of the T as a plus sign. So we took that T and made it like that. No. So the T looks like a plus sign now. And think of the N here as negative. But if you remember this one's easier, in my opinion, to remember than this one. If this is positive, the other one's got to be negative. So think of that T as a plus, or whenever you write cation, just make it your T like a plus. Okay, so when it comes down to one of these tables, like your handout today, you need a handout. Okay, so now this is the same thing as before. I supplied you with enough information for you to be able to fill in the blanks. But because this is an ion, all these are ions now. There's nothing here that's going to have a zero charge. Okay, because of that, I have to supply you with more information, one bit more information. It has to do with electrons. But if I give you this guy, you can calculate the electrons. Okay, so let's look at the first one. All right. We find boron, periodic table, right over here, kind of in the middle. What element is it? If you take out your periodic table from your lab packet, that's a pretty good periodic table. Okay, so boron is what? What element number? 5. And again, atomic number always equals number of protons. No exceptions. Okay, so atomic mass. We can still get neutrons and protons together equals atomic mass. That means that's 11. And you knew that because of this top number here. And so that's going to be boron 11. Now notice what's different about the symbol. Because the protons and electrons are not equal, we have to have a charge in there. And that charge reflects the imbalance between protons and electrons. And that imbalance is +3. +3 imbalance. If it's positive, that means we have more protons than electrons. And the charge number will tell you by how many. So we're up by 3 protons in there. So that means our electrons are going to be 2 less than 5. Excuse me, 3 less than 5. So that means it's going to be 2 electrons. Okay. The electrons are the only thing you can change, never the protons. Because once you change the protons, this is no longer boron. So the only thing you can change are electrons. So you match the electrons to equal the charge. Now, if I don't give you the charge, then you need to look at the protons and electrons. And whatever's more, it's going to be the charge, and the difference is going to be the number of that charge. Now, students find these, if my students do the first worksheet, this one isn't as hard if you've never done the first worksheet. Okay, so are there any questions? I'm going to do some more examples. Any questions about that so far? Correct. And you start with 5 electrons. So that means you have only 2 versus 5. That means the 5 is 3 over the 2. Okay, so let's do another one. Let's do 31. This one here. What element does that correspond to? Okay, so that's going to be gallium. All right. Atomic number of protons are always equal. Atomic mass is P plus N. So we have 31 and 37. What is that? 68. Charge. Now we need to look at protons versus electrons. Okay. So we've got a mismatch on protons and electrons. Hence we have a charge. We're looking at 31 positive, 28 negative. What do we have a net of? 3 what? We have more protons, 3 positive. Whatever's more, that's what this charge is going to be. So we have more of the positives. And then you ask yourself, by how much? By 3. Now you can write this plus 3 or 3 plus. When I was in high school, they taught me plus 3, and I've been doing it ever since, but most books put it down as 3 plus. But everyone, either one is recognized. So if you've never done charges like that before, do the 3 plus. Okay, and then what else is left? I have one more number to furnish. Yeah. Okay, because it's an ion, protons and electrons are not equal. Okay, which do you have more of? Hence that. By how much? Right here. So 31 minus 28 is 3. That's where the 3 comes in. In a neutral atom. An ion is a regular 2. It's just an imbalance. And if I don't say anything, figure it's neutral. A lot of textbooks won't say anything until they get to the ion part. But to me, I like to say it's neutral. What does neutral mean? Because it helps with the ions if you come up with this concept of neutrality. Okay, so we have one more number left, and that's the isotope. Okay, so let's do one more, and then I want you to practice this. Bless you. Let's do lead down here. Okay, so we have lead 207. 207. Okay, so now we need to fill in all the numbers. Now, if I gave you the symbol here, that's the atomic number or number of protons. So this 82 is going to go here and here. Okay, what about the number of electrons? Okay, the charge is positive 2. What does that mean? Two more protons. That means we have 80 electrons. And then neutrons, okay, remember P plus N is equal to 207. And we know the P is 82. So what's the neutrons? 82 plus what is equal to 207? What is it? Okay, so when you have a name of something like lead dash 207, there's no connotation of charge there. Only when you see the symbol over here. Sometimes people will put a charge here, but normally they don't. Sometimes they do. Okay, so why don't we spend 10 or so minutes and just practice some of these. Yeah. This guy here. And MO is molybdenum. And I don't remember how to spell it. Not something I work much with. But guess what came up when I put MO down? Mod pizza. You not believe when you Google search MO, do you know it's short for Moses? And it also means in Hebrew to deliver. Sure. Okay, anyway, let me borrow your table here. Okay, so all right, the MO molybdenum got a positive 1 charge. So how many protons does it have? 42. And that's the same as atomic number. And how many electrons does it have? 41. Okay, so a lot of things in science dealing with one. Sometimes it's optional, other times it's not. Like when we get into naming compounds, there's one is the prefix is mono. Sometimes it's required, sometimes it's not. So in this situation, the one is optional. And if you want to be totally consistent, put +1, but plus, just plain old plus works also. Okay, so what's left here? The isotope, it is 95. So 42 plus 53 is 95. Okay, so go ahead and spend another 10 minutes or so practicing these. Okay. Well, I just put the necessary numbers down. Blank ones are the ones you can derive from the existing numbers.
Mhm.
Okay. So, so the 95, this is always equal to,
These two, right? The protons and neutrons.
yes. Oh, wait a minute. This is, oh, yeah, that's right. I was adding these two. These two, P plus N
Mhm.
is equal to this.
Mhm.
You also know it's 95 because of that there.
Mhm.
And this number needs to be one less than this one. So you have more positives and negatives by one.
Mhm.
That's what the plus one means.
Okay. I get that. So if this is blank, and because it's a plus, it would be 42 minus 1. The positive is minus the neutron. Okay.
Yeah, so this charge will tell you which is more.
Okay.
And then the number associated with that charge will tell you by how many.
Okay.
And you can never change protons, always, no exceptions,
Mhm.
electrons. Electrons come and go, but protons, unless you're doing nuclear chemistry, stay the same.
Oh, so it is charged.
Yeah, and this can be positive or positive one. Better? This makes sense? Can tell.
I just want to make sure.
Okay, well, you need to fill these out, but
Yeah.
You have your lab packet?
I do not actually. Sorry.
You have a lab today?
No,
Okay, good.
I do.
I think I have an electronic copy of the lab for today.
Okay.
So home tonight, you need to do your write-up.
Yeah.
So just download that, but
Okay.
you need to pick it up.
Yeah.
The same thing then. Have you got your lab packet? No, it's okay. Remember what it costs? $6?
Oh, I already bought it. I just left it out.
Oh, all right.
Yeah.
So $6. Not too bad. Okay, so let me see. Now, these two together need to be 261.
Okay. So it'd be that doesn't. I would have to subtract 102 from 260 instead of
Well, let's see.
it'd be
Is that a 9?
yes.
Okay. Well, 59 and 2 is 61, so. Yeah, these look fine.
Okay.
Once you fill little details on. This making sense? Cool. He's filling in okay. All right. I think most of you got a pretty good handle on this. Yes. exactly. Exactly.
Do we have feedback write-up?
Mhm.
I actually just put it out the whole feedback thing as well. Copy down all of this.
Okay, one thing you don't have to copy is a background.
I didn't do the back. So I did
Okay,
the
good.
purpose and I did procedure. And then I did all of that, and then I did the pre-lab questions. Like this section over here, these ones. this
And you
is
can't do this until you do the
during
lab.
lab.
Yeah,
so,
but the
it
pre-lab
doesn't
questions you
matter
can't.
That I didn't copy all that down into.
No, you're gonna have to do a data table for this information,
Okay.
and you have to do it in pen too. So don't copy that though.
Okay.
Leave it in pencil. Just next time do it in pen.
So for the data table,
Yeah.
okay,
So whenever you, purpose of data table is a place to put observations or information like mass or volume or something like that.
Okay.
And it's usually a table.
so something like that.
Yeah, something like that. Now, the data, normally I recommend it, but I don't require it. You have to do it anyway. Yeah, that looks fine.
I was wondering, because I, the materialist, but I was like, data table, I don't know exactly how to do that.
You look in the procedure and they'll say, like weigh this, like they were gonna do a lot of weighing. So you need a place to put the mass in grams of what you weigh. That's what, also observations, another thing for data tables. So if it says record volume or mass, think data table, or observe data table.
So for equipment, though, is it just kind of like you just read through the lines and find that everything that's in there, or is there like a set of equipment notification somewhere?
The equipment, sometimes they give you a list of equipment, sometimes you have to paw through the procedure.
Okay, so this one's just the procedure. Oh, okay, I got it.
And if there's a setup also, it's nice to have a drawing of the setup.
Okay.
But the main purpose of the pre-lab is for you to be organized and get the lab done. I've substituted for other professors and they don't do this. And the students don't even know what lab they're doing that day. And they have a little handout and they write the answers down. No conclusions, no. And the lab is supposed to reinforce what we're learning in lecture.
So it would be good to bring one of these to it as well.
Yeah. But everything you write down is going to be in here though.
Thank you.
Yeah.
Do anything for the safety stuff for this one?
No, because I mean you can if you want, but we're having sand and salt.
Okay.
Anything that's food, don't worry about safety. And sand, unless you eat a lot of it
And don't get it.
or grind it into your eyes. Yeah.
Okay, so is this, I have the pre-lab questions and then the purpose. is
Yeah.
not
So what's missing is procedure.
procedure, okay.
And had we having worse chemicals,
Yeah.
the
and I
safety.
would think-
Exactly.
And with, in those labs, will there be like a list of like you're gonna be using sulfuric acid and this and that, and then I go online.
Sometimes,
or
otherwise
just to read it and be like, okay,
you
here's
paw
this.
through the procedure and go, oh, we're using sulfuric acid. Yeah.
Okay.
And then do the SDS for whatever, sulfuric acid, whatever. And various people have written these labs. That's why they don't look the same.
And so then I would just kind of like, I would just write this stuff in there. The procedure part.
Yeah, except we're not doing this lab.
We're
We're
not-
doing lab 4.
Oh, what's that? Okay, well,
This is a much more interesting lab than this also. This. Yeah, this is a really, how should I put it, boring lab.
well
And we
then,
skipped this one
I'll have to
because,
redo this.
oh, yeah.
Yeah.
So just leave this and
Yeah.
just start the next page over.
Okay,
And I
cool.
won't, you have lab today?
No.
Oh, I was gonna say, I'm not gonna do you. All right, we're doing lab 4 today, everyone. Percent composition. All right, let's go. Are there any other questions about this table? I can look at your pre-lab also if you'd like me to, before you go over there. Yes, remember we did, because of that one day, the Saturday people, I wanted to have a full day with me. So I said, we're not doing that lab. Did you already write up lab 3? Oh, good. Okay, we had a question, right? Okay. Huh? I have a video on it. And I talked about it in one of the lectures.
Okay, never mind.
Basically, the pre-lab is writing down title, purpose, procedure, and any safety stuff before you come to lab. When's your lab? Tomorrow or today? Okay. If you want to come tomorrow, that would be fine. And then just do this tonight. Or if you want to just come in and do the lab today, that's fine. I won't ding you on it. But I did, in fact, there may be 2 videos on the lab write-up. So go to modules. Go to modules, lab related. Okay, so let's go on. This is talking about how do you form an ion. Okay. Now, for stability reasons, groupings, and remember we learned 4 groups when we talked about the periodic table: alkali metals, alkali earth metals, halogens, and noble gases. Noble gases, again, I'll repeat this, very important, are the only elements that normally appear stable enough to be by themselves without hooking up with anything else to form a compound. Everything else forms compounds with other things for stability reasons. Okay, sometimes they form something called an ionic compound. Ionic compounds are composed of a positive and a negative ion together. Groups tend to form certain charged ions. So no charge for the noble gases. The halogens form a -1. So if you go back to your notes, when we looked at the periodic table, where you wrote down the groups, let's add to that these charges. So basically group 1, or the alkali metals, forms a +1, all of them. And remember, the groups all have chemistry characteristics alike. One of the reasons why they're alike is because they all form +1 charges. So that's why sodium and potassium are used together frequently, because potassium acts extremely like sodium, and it also forms a +1 charge. +2 for the alkali metal. So these are alkali metals. These are alkali earth metals, form +2. +3 over here, aluminum and gallium. And then this group here, group 4, is carbon. So you'd think we go +1, +2, +3, what would that be? +4, okay? Keep that thought now, all right? When we go backwards from the noble gases, the first group we run into are the halogens. They form -1 charge. The next group is the oxygen group. It forms a -2. Nitrogen group is a -3. So what should this one be following that logic? -4, right? -1, -2, -3, -4. +1, +2, +3, +4. So this group does nothing. It's not going to form a +4 or a -4. It does neither. So this is the group carbon is in. So part of the reason why the groups have similar chemistry characteristics is because they form the same charge. Now we're going to find later in the semester why they form a positive 1 charge, why they form a positive 2 charge, etc. So these are very characteristics. Now also, I mentioned we can form ionic compounds. We can also form, so these are, where do we go? I want, here it is. Okay. All right, so this comes into play when we have ionic compounds. Ionic compound is made up of a cation plus an anion. When we get into naming, we're going to find that the charge has to balance. So the charge sum of the cations has to be equal to the charge sum of the negatives. So if this is +2, that's got to be -2. So we have a net charge of 0 on an ionic compound. So in nature, if these are the natural forming ions, then these guys are going to naturally hook up with these guys. Okay, what's the formula for table salt? Sodium chloride. Okay, and remembering from the periodic table organization, those are the metals. And in blue are the nonmetals. So frequently ionic compounds are said to be metal plus a non-metal. Metals are usually cations, nonmetals are usually anions. So that's one group of compounds, ionic. And there's a naming convention, which we're going to go into in Unit 3. There's a naming convention for ionic compounds that's not the same as a covalent compound. So we're going to contrast ionic versus covalent. So in an ionic compound, electrons are actually transferred so that one is more negative than the other. In a covalent compound, electrons aren't transferred, they're shared. So those are the two naming conventions we're going to have. We're going to have a covalent naming convention, unfortunately, is different than an ionic naming convention. That is one of the big areas for 2A and 1A students, or 3A, is naming stuff. You have to understand the concept first. Ionic compounds have a cation and an anion, or a metal and a nonmetal. I like this better than this, because this you get into, it's a positive charge. This is the negative charge. This you have to remember, metals are positive and non-metals are negative. In this one, we're going to, both of these achieve stability in a totally different way, but they're both stable. So sometimes you can have a compound with the same formula for ionic and covalent, but they act differently. You'll find that ionic compounds conduct electricity really, really well. Covalent compounds don't. For example, an example of a covalent compound would be gasoline. Sodium chloride in water. Gasoline, you can throw electrodes in there and it won't conduct. Throw electrodes in salt water, it'll conduct electricity really well. What about water? Pure water. Do you think that's ionic or covalent? It's covalent. So that means pure water shouldn't conduct electricity. And it doesn't. What conducts electricity are the ions in the water that do the conducting of electricity. So if you're sitting in your tub and it's kind of nippy out and you have your little heater going on the edge of your tub and you're in pure water and it happens to fall in, no need to worry. Nothing will happen. If you got some other stuff in that water that's ionic, you're not going to be getting out of the tub. So covalent compounds, non-conductive, ionic, very conductive. Okay. Now, what I want to do is go into abundances of various kinds of isotopes. For example, let's look at oxygen here. Oxygen 16 has an abundance of almost 100%. So when you look at the decimal number for oxygen, it is it's rounded to 16.00. If you have more decimal places, it's 15.9999. It was really close to 16, and this is why it's close to 16, is because almost all the oxygen is the isotope 16. There's a little bit of 17 and 18, well below 1% on both of them. Let's look at carbon. The molar mass, or the decimal number for carbon, is 12.01. So the most abundant isotope is 12, and you can see it here, 98 or 98.89. And there's a little bit of carbon 13 and carbon 14. In fact, they don't even mention carbon 14. It's a trace. So what they do is, this is how they come up with the decimal numbers. For example, if you were calculating boron, you'd go 19.6% times 10, 80% times 11, and add those numbers together, and then you'll end up with 10.81. That's how and it's called a weighted average. The weight is the percent. Nitrogen. To get the decimal number on the periodic table, we'd go percent times this number here, percent times this number there, add them together. And that's how we get the decimal number for nitrogen. Nitrogen should be, was it 1401? Yeah, 1401. So most of it's 14 because it's 99.6%. That's why it's closest to 14 when you do the average. And again, we're doing a weighted average here. Another concept that 1A and 2A students incoming lack that understanding of what is a weighted average. It's this percent, this percent, this percent, add them together. How to get that. So we look at these decimal numbers here, that you can't read very well. That's where they come from. And again, it's the weighted average. So we take the percent times the actual mass plus the percent times the actual mass, add them together, and that's what we'll end up with 3545. Now, who's heard of the term radioactive? Most people? Okay. Everyone thinks of it as can be bad. We have a nuclear power plant accident or atomic bomb goes off or whatever. People usually think in very negative terms. Radioactivity is when one element, one isotope wants to become more stable. So it does that by emitting subatomic particles like a proton or a neutron or a positron or an electron. And then it changes to a new isotope, which is more stable. And sometimes that isotope is short-lived. It isn't all that stable, so it continues on that stability. And if you trace the number of if you trace the electrons, neutrons, and protons and elements, they fall along a line. And it's the ratio of protons to neutrons. One ratio is more stable than the other. Usually it's a 2-to-1 ratio. So the slope of this line is 2. If it's out of the 2-to-1 ratio, it becomes more unstable and starts to give off subatomic particles. And that's what radiation is when an element becomes more stable by emitting stuff. You can also capture stuff. Most of the time you're emitting stuff. Has anyone had a PET scan in here? You know what it stands for? Called positron emission tomography. A mouthful. And basically, a positron is the exact opposite of an electron. It's antimatter. Sounds like Star Trek. And when antimatter counterpart collide, they produce pure energy. So on Star Trek, old Scotty's jacking up the antimatter stuff to get more energy out of that engine. So a positron emission tomography, PET scan, actually takes a chemical that emits positrons, and that chemical will migrate to whatever they designed it to, organ they designed it to go. What organ were they scanning with you? Oh, you're okay. So chemicals, when his scan, the chemicals will go to his brain. And then there is a detector around your, in this case, around your head that detects when that positron goes off and collides with an electron. Boom, a little explosion. And then this 3-dimensional detector on a computer puts its coordinates down. Then after you do that, it'll end up with a 3-dimensional image of the area where the chemicals went. And PET scans are expensive. That's why a lot of people don't get them. It's similar to a CAT scan, only it's much more specific. Like my friend is recovering from prostate cancer, and they discovered it with a PET scan. So as far as subatomic particle goes, there's protons and neutrons and electrons. There's an electron inside the nucleus. Electrons are buried inside of a neutron along with a proton. So proton and electron together form a neutron. And that's where the electrons are coming from when you emit a beta particle, which is an electron. There are also positrons in there as well. So it's interesting. So anyway, along the black line there are the stable isotopes. The white areas are the unstable isotopes that want to become more stable by either emitting a particle or capturing a particle. Sometimes they call that bombardment. For example, to start an atomic bomb, you bombard uranium-235 with a neutron. And then it splits in half into barium and krypton with tons of energy. And then there's a chain reaction that keeps it going. And with a bomb, you don't want to control it. With a power plant, you do want to control it. So you cut down those neutrons to control how much energy is given off. But anyway, that's what radiation is that stability bit again. How do you become more stable? You want the ratio of protons and neutrons to be that magic number. So you keep fussing with it and it becomes more and more stable. For example, well, there's a lot of examples, but anyway, so that's the concept of radiation. Stability again. Okay. They're saying lead-185 emits a significant amount of radiation in a very short period of time. That means it's very unstable. There's a number called half-life. Half-life is defined by the amount of time the initial mass turns to half of what its original mass was. Hence it's named half-life. The shorter the half-life, the more unstable the isotope is. So lead-185, very short time. This can be like milliseconds or nanoseconds. And it gradually will start to go away. Have you heard of carbon-14 dating? Some of you have, some of you haven't. That's a way to determine the age of living things, because living things take in carbon dioxide, give off carbon dioxide. So they take in oxygen, give off carbon dioxide. And the amount of carbon-14 left over is a function of the age of that. This is plutonium-239. This is a stuff that is thousands, millions, billions of years to form a half-life. That means if you start out with a pound, it'll take thousands and thousands of years to get a half pound. Plutonium is one of the most poisonous substances on Earth. Nanograms will kill you. And we're talking about pounds. Hanford, Washington. This is where the Manhattan Project got some of its plutonium from. Massive. My first wife got a job offer to move up to Washington for Hanford. And right now they're looking at $3 billion a year cleanup fees. Everything around there is really contaminated. So bottom line is this is super stable. Why is it so stable? Because the half-life is really, really long. This is super unstable because the half-life is really short. It wants to become stable. Quicker, the better, the more unstable it is. Okay, so. All right, so I'm going to stop here for today. And then tomorrow I want to get into atomic theory. I'm going to start with the Greeks. I'm going to build to our modern model of atomic